Thank you. This should be called the pre-lunch talk, more likely. All right. So I'll tell you about the work that we have presented recently in February. If you've seen that talk, you can tune out until the last slide where I'll give you a little bit of updates of what has happened since then. We got the usual assortment of graduate students, but I want to highlight that we have high school students. As far as I know, this is the first ever FAST paper with a high school student. It's definitely a first for me. So NFS is very, very old. It's, decades old. In V4, it got standardized as the ITF standard. It provides, transparent access to remote files. But historically, we all know it had really poor performance over wide area networks. Basically, the model is clients talking to server. Nothing, old news here, right? NFS version 4 codified a lot of ideas of how to improve performance over wide area networks. And one of the things that they added is something called compound procedures. So first, let's see what the issue is. In the old days, you had slow networks or thin pipes and slow disks. So, every request had to go all the way to a slow disk and then wait for the platter to rotate and then come back, right? But nowadays, we have thicker pipes and we have flash disks, so things go much faster, or can go much faster, but still we're doing this one call and coming back, wasting a lot of bandwidth. So what NFS version 4 said, well, we can basically batch a bunch of things all in one big message, but put a bunch of operations, send them as one big message and come back. In the networking world, this is old news, right? Bulk updates are better than individual messages. But the problem is that compounds are really underutilized. And one of the biggest problems is that the POSIX API, which is even older, is very serialized. It asks you to do one thing at a time, right? So let's see an example of what happens when you try to read your bash RC when you log in for the first time. How does it happen on NFS? This is an example from Linux. So first you have a message. You do stat, so you get the lookup for home. You have to wait to get the attributes for that. And then you do lookup for Bob. That's already 2 messages. Then you do the actual open of the file. Then you do the read. But wait, that's not over. Then you have to do a close because it's a stateful protocol. So you have to do 5 messages back and forth. Ironically, Linux actually uses compounds inside the kernel, in their Linux client. You see that they actually do 4 different operations inside a single compound. This is basically setting the file handle for the next thing to happen, then looking up. This is the file handle for the root / and then getting the file handle so you can do an attribute on it and finally returning the attributes. So they use it, but in a very limited fashion. And what we really want is basically to take all of this and create a kind of an API that allows you to pack all these messages into one big message, and then send one thing and then return only one thing instead of like having only one off back and forth, one round trip instead of 5. And that's effectively what we did, and I'll show you how we did that. So first we have to figure out what will be the right API for this. So we looked at a lot of traces, applications, our own experience. We figure out what are the kinds of things that people do often. And we've implemented a bunch of these vectorized APIs. The most obvious thing is to do a bunch of reads and a bunch of writes at once. Kind of similar to read v and write v, only the read v and write v actually require you to do them in sequential units. It has to be all contiguous blocks of reading and writing. Here we have something that allows you to read and write any chunks of a file, not necessarily contiguously. We also automatically allow you in this API to open the files and close the files. Those are kind of wasted things that you have to do, but we do it for you internally. The actual implementations, the way it looks like is we create a structure that keeps the information, and then all the calls look like something like there's an array of the structure and the length of the structure. So the prototype for all these calls looks pretty much the same, and there's even a way to implement additional ones fairly easily if you want to. Now, in addition, there's a lot of attributes. We're getting a lot of attributes. Has historically been shown to be something that NFS does a lot. And also setting attributes. This is useful when you do a lot of recursive operations, tarring, rsync, copying. Those happen to be a lot of attributes. In fact, both inside the Linux kernel, the VFS and the NFS itself, they no longer do individual like chmod, chown, utimes. Everything gets basically funneled into one system call, or one internal operation for setting attributes. They found that to be more efficient. The next obvious thing that we found happens a lot is copying. Lots and lots and lots of file copying. What happens normally when you try to copy a file is you read some bits and then you write them. You read them and you write them. It's very expensive, lots of round trips. So we implemented two versions of this. The first version is do bulk reading and then bulk writing. So yes, the data does go all the way to the client and comes back, but at least we're saving on a lot of latency or round trips. Then as we were implementing this system, and we implemented it in NFS 4.1, we found out that in the upcoming 4.2 standard, they added a new message or new operation called copy, which will allow you to do server-side copy directly without ever shipping any bits to the client. So we actually backported this implementation in order to be able to compare what are the benefits of doing this kind of copy versus the server-side copy. We did a bunch of other operations like being able to open and close for large files where you can perform operations on them, symbolic links, hard links, creating directories recursively. Our code allows you to ask what you want. For example, you can say, I want to create a directory ABC. Internally, we're going to break it down and map it to what the protocol wants. And in the protocol, you cannot say create a directory tree directly. You have to create each directly separately. So we have to break things into create A and then create B in A and then create C inside B. We do all that stuff internally for you. And of course, removing, renaming, a few other things. The architecture is as follows. Applications will issue requests to our user level library that gives you the Vectorize API. If there's anything it does not recognize, it immediately just calls a regular system call. So this way you can inject this library into your applications and transparently you'll improve whatever it can improve. Otherwise, it's just completely compatible with POSIX. One of the ideas is how would people use this in the future? How would you start to use it for real applications? And then the idea is to kind of allow incremental changes as you improve this library and applications start to use it. And of course, anything that we recognize as an NFS call or our own API, we ship it to our own client, also in user level, which then creates its own network RPCs, goes to the networking stack and all the way to the server. The implementation of this, we use NFS Ganesha, which is an active project that has an NFS client and server and user level. It's all C++, open source. We actually submitted a bunch of patches which got integrated. We've helped them in several ways. They've got a nice abstraction layer that's kind of similar to the notion of a VFS inside NFS Ganesha. It's actually kind of a stackable layer that you can inject things and stack them on top of each other. So this allowed us to implement these additions fairly easily. Our client is basically code that we extracted out of NFS Ganesha and kind of created a client library that can create its own RPCs and ship them directly. And we created a library. As of fast, when we presented it, we didn't have a cache yet. And I'll show you the results without a cache, and then I'll talk to you a little bit more about that. And then the server side is just a stock NFS Ganesha. However, we added two things. One was the server-side copy. We backported it from the 4.2 protocol, and we also added atomic file appending, so you can, a lot of applications want to append large chunks to files. The total code is about 10,000 lines of code. If you're interested, it's all available on GitHub. Our evaluation is the two machines are actually not terribly new machines. The server is using SSD. We measured the network latency between these machines as 0.2 milliseconds. That's the fastest that we can send packets. And we're using NetM to inject additional delays to emulate what will happen if you went to sort of longer and longer latencies. We measured latencies in our own town, going to the next city, going to New York City, all the way to California, and then there was a range of latencies going all the way to 100 milliseconds. We benchmarked using micro benchmarks and a bunch of general purpose benchmarks. For time considerations, I'll only talk about some of them. There's a lot of results in the paper. So let's get to some results. This is recursively copying or GNU-CP. So first, what are we seeing here? The y-axis has the running time, higher is worse in seconds. The x-axis has the latency of the experiment, where this is basically the baseline, the fastest we can go, and we go up to 5.2 milliseconds. And then we have three bars. The first, or red bar, is the baseline. Basically, this is the Linux NFS client, unmodified application. The green is with our own vNFS, but without the server-side copy. And then the blue is with the server-side copy optimization, because in this CP-R, you're going to be copying a lot of data. So what do we see? First, we see that you get, even on your LAN, a 4x performance improvement. This actually completely surprised us. We thought that there will be a crossover point. We thought it's going to be slower on the LANs because there's extra overhead of all this extra processing, and above a certain threshold, we're going to start to see improvements. But by and large, we found that it's beneficial even on the fastest networks. So even if you're not planning to use NFS all the way to some faraway place, this technique is still beneficial. Now, server-side copy gave you another 2x factor on top of the improvements. And when you go to 5 millisecond, you get already 60 plus performance factor. This is already 50 minutes of runtime. A lot of the experiments, we had to wait for this to finish. And we're talking about hours and hours of runtime for repeated experiments. So what I'm going to do from now on, I'll only talk about speed up ratios over the baseline. And this is an example of basically recursive LSCP and removal. And on the y-axis, we see a log of the log base 2 of the improvement. And on the x-axis, we see the network latency in milliseconds, but now we're going all the way up to 30 milliseconds. So this is basically state to state kind of, at least for us from New York. And you see that, you get anywhere from 2 to 200 plus improvement in overall performance, especially when you go up to latencies that high. The total amount of code for modifying core utils, we're talking about a few hundred lines here and there. This is something that a high school student could do, so certainly your highly paid, highly educated employees can do. Next, I want to show you the impact of what's called compounding degree. The question is, how much can I pack into a compound, and what's the impact as the compound, the number of messages within a single compound grows? So again, we have speed up ratio log against the baseline. This is 1. And the number of operations that we put in a single compound also log, starting from 1 in powers of 2 all the way to 256. We have 4 different workloads here. This is like writing 4K, setting 1 attribute, setting 4 attributes at once, and then reading 4K. And what you can see is that, we get comparatively and even slightly better performance even on a single compound on this fastest network. So if you go to a slower network, all these things will go even better. Overall, you see, again, we get pretty good, improvements of overall performance in the range. It's much better at the high end when you get like hundreds of things packed into single messages. There is a couple of things to note. First of all, things tend to flatten out here. And the reason is we have reached the maximum limit of the RPC message size. We can't go any bigger than that. You need to do sort of fundamental changes to the RPC layer to allow bigger messages to go. And the second thing is we did get slight degradation in performance for setting 1 attribute and only 1 operation within a compound, because there is still some overhead to adding all this processing, and then everything we still are doing in user level, and this is not highly optimized code. We did some Filebench workloads. We did, the NFS server, file server, and varmail. Varmail sees the best performance improvement because it's kind of very I/O intensive, got lots of reads and writes in there. The other ones are more metadata intensive, but still they see good performance improvements. Few hundred lines of code that we changed in Filebench to interface directly with the library. The last benchmark I'll tell you about is the HTTP2 server. And the interesting part about here is the following. HTTP2 actually supports a compounding. That is, you can send multiple URLs at once to the server and get a bunch of results all at once. So somebody already thought this is a good idea. So a web client can issue a bunch of HTTP gets at once and get a bunch of HTTP results to the server. Now, what if the server were an NFS client to an NFS server? So that basically the storage is not local to the server, but it's starting to be farther and farther away from the perspective. And we were using our vNFS library with some workload that we measured to be sort of a realistic enough workload. So you find that you get anywhere from 3 to almost 10 times better improvement in performance, end-to-end performance for this. And the changes here were, again, on the order of a few hundred lines of code, nothing terribly significant. All right. So in conclusion, we basically created a system that makes NFS more useful by basically compounding more things into one message, give you a bunch of useful APIs and a way to create your own. And we didn't have to change the NFS protocol at all, and we didn't have to change the server with the minor thing that we backported a v4.2 server-side copy feature. All of this is implemented in user level. At first we started to work in the Linux kernel and realized it's way too messy how they've done the NFS code and way too difficult to do it. So we figured, let's do it in user level and see how much we get. Porting applications was not terribly difficult at all. And if you get performance improvements on the order of hundreds, then I think at this point people will start to say, well, then it's worth for me to spend the effort to change my application because nobody wants to modify their applications normally. And we feel that we've essentially made NFS usable on high latency networks, sort of the premise of more than 15 years ago when they created the very first protocol. The surprise was that it helped even low latency networks, and we think that will be a hook for a lot of people to want to use something like this. So before I finish, let me just tell you about a few limitations in future work. We've implemented a caching layer for our library, and early results are that you get 2x performance on top of everything just from caching. This is, by the way, only data caching at this point. We're now working on implementing metadata caching as well. So we expect there will be even more improvements. We are now working on transactional semantics. So now if you can pack a bunch of messages all at once, we want to see if it's possible to allow end-to-end transactional semantics. There's a lot of good reasons, reliability, security, and so on, to allow transactional semantics. For that, we need to change the protocol a little bit by creating another major procedure that is called basically a transactional compound. It's essentially, we just need one more bit in the protocol to say, this is not a regular compound, this is a transactional one. The bigger changes are on the server side. And the way we're currently looking at implementing it is using copy on write mechanisms with BTRFS, because you have to have the transaction and the atomicity go all the way through the file system layer on the server down to the storage. So that's where the biggest challenge, and we're working on it right now. And the last thing is we're actually looking at changing, or what would it take for people to use this in the future. And we think that you have to really change the POSIX system call API itself. It's old, lots of people have complained about it, but no one wants to do anything about it, like the weather. And so we actually are going to be presenting a paper at Hot Storage about this general idea about, basically new kind of POSIX, throwing away POSIX and what will be the right new model. That will be interesting to think about it. But this is something we're working, because we think that if you want to really make the most out of this idea of compounding, you have to basically allow a new system call API that would somehow let users pack more things into a single message and not basically issue a bunch of individual system calls. And if you do this, then you can translate that end-to-end all the way to the server storage, to the storage, and all the way to the server if your storage is far away. All right, that's what I have. I can take a few questions. Yes.
Okay, this is very interesting as you're trying to maintain backward compatibility, but there is the object store that can address many of these problems for some of the workloads. So if in your hot, cloud systems paper, I think this is something you should consider, especially if you're changing the POSIX.
So the principles of compounding apply everywhere, including any kind of remote object store. We actually have a different project that does something that can translate to NFS or object store, and we've seen similar benefits if you can basically send a bunch of object requests all at once. So absolutely yes, that you would get the same kind of improvement, because it's not really the protocol, but the idea of just eliminating a bunch of round trips. Simple idea overall, right? Yeah.
It's kind of a similar, if someone has something else.
Any other questions?
Yes.
I just want to say, so I'm a programmer and I'm lazy. I don't want to change my application. So I'm just curious if you've thought about implementing, like basically transforming the program into a batching program, either with a binary or using a compiler, maybe like doing some kind of lazy evaluation.
Yeah. Basically, it's a classic question of this. People have looked at it. We've done a lot of work, for example, in transactional file systems and transactional storage, and there's various ways. Give you a completely new API or allow you to mark the begin and end in your code. We actually had a project way back in 2003 called Compound System Calls, where what we did is we allow you to mark the beginning and end of a program, a C program, and with a compiler-based technique, a modified compiler would parse the code and see if it's possible for it to pack a bunch of these and send a single message through a new system calls that will issue all these system calls at once. So yes, it's absolutely possible to do some of this through compiler techniques, and I think that could be sort of a first round that might allow people to take existing code and see how much can we get. But I'm absolutely certain that at some point you probably want to change your code, because there's some code that's just too complicated that it would make more sense to change it.
Yes, there are a couple of questions in the back.
So it seems like you compound requests that normally when I write my program, I will try to catch failures for each one of them. So what if one of them fails? For example, we want to create a directory A inside B inside C. Now C failed, but A and B succeeded. Now, do you keep some kind of state of the machine from the beginning, or generally how do you deal with it?
So the failure semantics of compounds in the NFS core protocol is when one of these messages, when one operation in the middle of a compound failed, they stop and return whatever results they got up to that point. It doesn't undo any of the state. That's why we're working on transactional semantics, because there's enough people that want to be able to issue these things all at once. Classic example, you want to update Etsy password and Etsy group at the same time, and I have halfway changes. So you're absolutely right. That's kind of the next step.
Okay.
Have you looked at all at how much performance benefit you can get from optimizations on the server side by having more information at the server? For instance, not having to move, having information to cache, or not just the chattiness, but if you're doing a whole bunch of things, you may be able to use that knowledge.
So we one precursor to this work was a paper last year in Sigmetrics where we wanted to see just how bad or good is NFS 4 depending on various factors, unmodified, completely unmodified. And so we found out that the server-side storage, for example, became a bottleneck at some point. For example, when we had 1 gig network, it was very easy to saturate it. So we moved to 10 gig network. Now we were able to get more from the client to the server. Then the server-side storage became a bottleneck. So we started to optimize that and found that if we put like 8 SSDs in parallel, we were finally able to get something like 85% of the 10 gig network throughput. So there was a series of optimizations to be able to get to what is the best I can do with just an NFS server on the local network. The difference here is that once you start to inject even 1 or 2 milliseconds of latency, it really doesn't matter what the server does anymore, because that's almost in the noise in terms of its latency, and the big bottleneck is the network.
Now, after you've done your compounding, get to the server, because that now opened up a lot more opportunities for optimizing on the server side. So is there another?
Oh, okay. So you're saying maybe the bottleneck has shifted somewhere to the server now, and then we have to look at what's there.
Optimize, but you have more knowledge of the stream of operations.
Yeah, that's a good point. No, we haven't done anything like that. Yeah, you're right.
Any more
Also,
questions?
maybe how this affected the scalability, maybe how it somehow affected scalability of the NFS.
Yeah, that's a good question. Where are the bottlenecks right now? A lot of us who have started to work with, for example, NVMe have noticed that workloads that used to be I/O bound all of a sudden become memory or CPU bound with the right data structure. So I think you and Michael are right that the next stage might be to see if there's any extra optimization opportunity to serve any bottlenecks there. That's a good point.
There was a talk in MSST about campaign storage. If you heard about it, Peter Brown's work, they also there is a lot of concern that POSIX is not good enough for today's system. So this is very
Yeah, definitely POSIX has some major issues.
One last question.
Bit of a provocative question to some extent. You talked about transactions. Databases have supported batching and transactions forever. Are we effectively turning this into, relational database kind of thing?
Key value store.
Key value store, right?
Yeah.
Yeah.
That's what you're doing. You have to
Yeah.
change the applications. You have to change the servers. You're going to have to change the protocol. You might as well just move to something that's going to be way better because it's not been designed.
There's actually been a question that a lot of people are asking now, which is do we even need a file interface anymore? Some of you know this. Namespaces are dead paper by Margot Seltzer, and some people are saying no, it should be a database interface, a key value, no, an object store. So
all I'm saying is that that's what you're doing here. Anyway, you're clawing your way over a very old protocol. Forcing people, not forcing, no one's being forced to anything, but to get a benefit, you have to change and recompile your programs.
Yeah.
I don't know what it does to the security. I'm not sure I want to use the web server where you had to change all the open to vOpen. I don't know what it does.
Yeah.
And that thing should have been a key value store for sure, or an object store. So I don't know. It looks like it sits somewhere in the middle between like a file system and I'm just not sure where.
Yeah.
And I think that's a valid, where is it? Who is this for? I don't know. I'm not saying it's not for anyone. I'm saying I don't know who is.
No, I agree with you. I think it's if you already have the idea is if you modify these applications once, not everybody will have to modify the application, right? If I modify GNU QueryTils, it's done once, and then everyone can benefit from it.
I agree. I just modifying applications, especially core ones, especially security with networks and so on. It's not clearly easy.
In terms of security, I totally agree with you, which is why we're looking at transactional semantics for the reason of security, because POSIX is replete with talk-to bugs. There's been a bunch of papers on that. That's one reason why we want to do transactions and actually starting to think about obsoleting POSIX, like I think a lot of other people have done.
All right, so let's thank our speaker again.
Thank you.